Okay, good morning, everyone. How did the graphing go? Were you able to graph using the approach we did in class yesterday? Sarah, can we do 29 and 32? Definitely so. Any other questions beside those? Okay, so we start with them. So we start with 29. Let's see what it was. R equals, so I'm going to try to do like yesterday, put the paper this, so I can draw both graphs at the same time. So I start with 29, and R is -2 sine theta. Okay, so we're going to graph this function. So as I said yesterday, I usually do two graphs. The first one is what we call, it's just the Cartesian plane, the regular old graph. It means I'm graphing R as a function of theta. So you can think like I'm graphing y equal -2 sine x. Don't let R and theta. So I call this the Cartesian R theta plane. And in this plane, I just want to know how is theta R changing with theta. So this is my theta, and this is my R, which is -2 sine theta. And in here, the R is the the vertical distance from the theta axis to the graph. And in the polar curve, or the polar plane, it will be something different. So -2 sine theta, we have to remember how the graph works. Now we know how sine theta is. That's the sine of theta. The sine of theta. The 2 sine of theta is just stretch this by a factor of 2. Minus will flip it. So -2 sine theta will be the following graph. So it starts at 0. There is no shifting. Because I have a minus, I will have to go down, and then I'll go up, and then I'll go back down. And after that, as theta keeps going, the values of R keep repeating themselves. So this is, as I said, the Cartesian R theta plane. Okay. And we definitely, absolutely, we have to mark some points which are relevant to the graph. So right here, something happened, of course, that's the pi over 2. The R goes from get more negative to less negative. This is my pi, the R is 0 here. This is my 3 pi over 2, and right here, R takes the value 2. Right here, R is -2, and that's this, sorry. R is 0, so theta here is 2 pi. Okay, so this is just the Cartesian plane, nothing more, nothing less. Now I'm going to take this piece of info from here and translate them to the polar curve. So now here I have, that's the polar plane. It means right here, for me, this is the line theta equal to 0. That's the way I see it. This line here, for me, is theta equal pi over 2. So I'm not looking at those as the x and y axis. I'm looking at this as the line theta equal to 0. If I take any point on this line, the theta is 0. I take any point on this line, the theta equal pi over 2. It's also 3 pi over 2. It's also 5 pi over 2. But I just picked one of them. And now I'm going to start moving info from here all the way to here. On this graph, the R is the distance from the origin, from the pole to the point. That's what R in this graph. In this graph, R is this horizontal distance. So once we understand this aspect, it will become slightly easier. So let us see. When theta is 0, R is 0. Right there. The other important point seems pi over 2. When theta is pi over 2, r is minus 2. So when theta is pi over 2, the r is right there. So I'm going to erase this point because I don't want this to be confused. So at theta 0 here, at minus pi over 2, I am right here. So this point is basically minus 2. Remember, everything here is in polar coordinate, and pi over 2. These are polar coordinates. Just make sure we focus on that. Now, what's happening from here to here? This picture right here. As theta goes from 0 to pi over 2, it means as theta go through this region, my r is always negative. So if theta takes pi over 4, my r is right here. It's negative. Theta takes pi over 3, my r is right here. So instead of having a graph here, the graph is going to be totally in the opposite side too. So at 0, I am here, and my r is getting more negative. It means the distance from my origin is actually kind of increasing. So I was at 0, the distance is increasing, the distance is increasing, but it's in this quadrant because r is negative. The distance is increasing, so as theta go around this region, my point are right there, and my r is increasing, my r is increasing, my r is increasing up to here. First piece of the problem. So this is 1 here, that's the piece of 1. Now we keep moving. I am at pi over 2. Now between pi over 2 and pi, what's really going on? At pi over 2, I am right here. At pi, it's 0. So at pi, I am here. But the question is, what's going in between? Again, so now theta goes from pi over 2. That's the region that theta is going to. But for r to satisfy this condition, every time theta is between pi over 2 and pi, my r is negative. So if theta is here, the r is here. If theta is here, the r is here. And what is r doing? R is getting less and less negative. So less and less negative. It means the distance is becoming smaller and smaller. In this graph, r is the distance to the origin. So r is getting smaller and smaller and smaller. I am right there. So this is piece 2, and this is piece 2. Then what's happening? Between pi and 3 pi over 2. At pi, I know I am at 0. 3 pi over 2, I am at 2. I'm right here. And between pi and 3 pi over 2, it means as now my theta goes from here all the way to here, my r is behaving nicely. It's positive and it is increasing. Now the symmetry of the graph, if you guys know that there is so much symmetry that the values of r are going to repeat themselves. So this r and this r are almost equal. The value of r are repeating themselves, so the graph is going to actually go around itself. So it reached this point between pi and 3 pi over 2, the graph will go around itself. Between 3 pi over 2 and 2 pi, at 3 pi over 2, I'm here. At 2 pi, I am here. And in between, my r seems to be increasing. Seems to be decreasing. Decrease, decrease, right there. So this is the graph. It's actually an honest to goodness circle. We can show that it's a real circle. All right, please ask questions as I am moving on. But as I said in class, this is the part that I really wish I was with you, because I usually let you work on those in class because of difficulties. So ask questions as I am moving on. All right, now we look at number 32. Okay. And I will be doing exactly the same approach. So first let me write the function 32. R is 1 plus 2 cosine theta. So I have to sketch all the points such that given theta, that's the value of r, very specific point. So I would like to know how is r changing with theta. So first I would start with the Cartesian r theta plane. So that's the Cartesian r theta plane, which I mean is that in this part of the graph, this is theta, the regular theta, and this is how r changing with theta. So instead of plotting point, I mean, that's really what we're doing. I cannot plot a million points. So that's really, this is rather easy. Now, how does the graph of 1 plus 2 cosine theta looks like? Can you guys sketch this easily? If I am doing it, I start with 2 cosine, which is just like the cosine. How does the graph of 2 cosine? It's exactly like the graph of cosine. It means it starts right here, but it's stretched by a factor of 2. So this is minus 2, this is 2. Pi over 2, pi, 3 pi over 2. The 1 plus will take this graph and shift it by a unit. So this x-axis is going to be shifted by 1 unit. So let me shift a little bit the x-axis because it orients me a little bit. And then everything else is shifted. So the minus 2 will become at a minus 1. The 2 will be shifted up to 3. And my graph would look, we start from here. There is no flipping. Is going to look something like that. And then it will repeat itself. So the values of our repeat themselves. Now, important point that always I like to see, this is, so the pi over 2 here was shifted by 1 unit. So this is the pi over 2. This is the pi right here. This is my 2 pi. And right here is the 3 pi over 2. Okay, now I need to sketch this. So before I sketch, what should I figure out? What's gonna impact the graph in polar right here? What's gonna impact the graph? So this is theta equals 0. And right here is theta equal pi over 2. Okay, back to you. Which point do you think will play a role in the graph? Which value of theta is important? 0 important, pi over 2 pi, 3 pi over 2. Those really are interesting points that we're going to take care of, but there are some points where it's going to play a role in the graph. Which point are those? Anybody can tell me on chat. Anybody? Okay, you're not in a talking mode. Right, where r is 0. Those are crucial. Those 2 points are crucial. So before I actually even move here, I want to know exactly where r is equal to 0, because at this point the r is positive. So I understand a little bit how to draw that. But the minute r become negative, I have to know that, because I know that I'm going to move quadrant. I will be working in the opposite quadrant. So before I even start here, I start by finding when r is equal to 0. So we're going to set r equal to 0. It means which value of theta will take r equal to 0, because at first here I am at the origin, and then something interesting happened because r will become negative. So we set r equal to 0 and we solve. So this will give me 1 plus 2 cosine theta equal to 0. It means cosine theta is minus a half. And the question is, if this is the value of cosine, what is theta? So which angle have cosine minus theta? Now you can use your calculator, or we go back to our unit circle. So that's my unit circle. The cosine is the x-coordinate. So if this is minus a half, that's the x-coordinate, I am basically after this angle, right there. And actually there's another one. And the picture shows me there is another one. So I am after this angle and the big one. So how can I find this angle? One way is use the idea of reference angle. Go back here to 1/2. Now, which angle has for cosine 1/2? Do you guys remember? Means which angle have cosine 1/2? Anybody? Please speak up. Pi over 3. Yeah, pi over 3. So this is pi over 3. So cosine theta minus 1/2, it means theta is pi minus pi over 3. Because this is pi over 3, this pi over 3. So which gonna give me 2 pi over 3. And the other one, which is this one, is pi plus pi over 3, which is 4 pi over 3. So I first start by finding those, because otherwise I cannot really sketch a good graph here. So those points will be, this is the 4 pi over 3, and this is with, sorry, this is the 2 pi, and this would be the 4 pi. All right, one more step before we graph. The second step we should do is I will draw the line that corresponds to theta equal to pi over 3. So before I even graph, so we'll have very good understanding of how the graph would look like, I will immediately draw the line where r is 0. So this is the line 2 pi over 3. Means the angle from here to here is 2 pi over 3. Similarly, I will draw this line. It means this is the line theta equal 4 pi over 3. Means from here, from the polar axis up to here, 4 pi over 3. So that's the first step I do before I even start graphing. And now we will be able to graph in a good way. I start. For theta equal to 0, r is 3. Means if I plug in 0 for theta, I will get 3. So theta equal to 0, it means I am right here. R is 3, that's a positive number. So that's the first point I pick up. So r is 3, theta is 0. Every coordinate here is in polar. Every coordinate is in polar. Pi over 2, because it's nice to solve. Theta up to pi over 2. At pi over 2, r is 1. Plug in pi over 2 here. You have cosine pi over 2, which is a 0. R is 1. So right here, that's the point 1 in polar, pi over 2. And between here, my r, which is in this graph, this distance, is actually decreasing. So this is my r. I want to draw those in red, so I will not confuse them. So I want those. And those also in red. So I can focus more. Now, between pi over 2 and 2 pi over 3, I stop when r is 0. At 2 pi over 3, r is 0. Between pi over 2 and 2 pi over 3, it means as r go from here all the way to here, my r, it means this distance is decreasing. So I'm going to have this graph. So far it's not bad because r is positive. Now what's happening here? At 2 pi over 3, I am at 0. At pi, it means when theta is pi, r is minus 1. R, it means I am right there. So that's the point in polar coordinate minus 1 and pi. And when theta is in this piece, it means that theta starts varying from 2 pi over 3 to pi, the point is right here all the time. So the graph is not in here. The graph is in the opposite side. And r seems to be sorry, I'm here. R is getting more negative, it means the distance is actually increasing. So I am right here and the distance is increasing, my graph will turn around. So the graph is not here, the graph is here because my R is negative. Now I keep going. That's why the importance of those lines, that's why they are so important. So they guide us. Now between pi and 4 pi over 3. So now my theta is between here and here, right here. Every time I take theta here, my R is negative. Every time I take theta here, my R is negative. Means my graph will be right there. And R is getting less negative. It means in absolute value, it's getting smaller. So it's gonna do this for me. And finally, the rest will be relatively simpler because R is positive. So now when R is between 4 pi over 3 and 3 pi over 2, at 3 pi over 2, I am at 1. It's increasing, it's in the same quadrant as theta because R is positive, and then it will turn all the way around. All right. So with practice, it will be much easier to do that. Okay, now we look at your last question and then we proceed, but this is actually crucial for us to be able to proceed, understanding the picture. So actually I should scan those, I think. So I'll number them so I know that I should scan them. So I'll do now the last problem. And this is, which one you guys asked? Act like asymptote. I mean, you can think of them like that. It's not really it's a good idea way to think about them. Yeah. Can we do number 30? All right, sorry. What's number 30 is about? Oh, R is theta. No, what is? Oh, did I switch? Whatever. R is 1 minus cosine theta. All right. Again, I will do the same thing. I will sketch the graph. And right here is the polar plane, which when I think polar plane, it means for me, this is not really the x-axis. This is where theta takes its value 0. And for me, this is where theta takes its value pi over 2. That's how I think about this plane. And this is the origin. Now 1 minus cosine, so this is the Cartesian r theta plane. Means the value on the horizontal axis are the theta value. The value on the vertical axis are the r value. And how does 1 minus cosine? So on the side, I do minus cosine. Minus cosine is, okay, cosine start from here, minus cosine start from here, and goes like that. And I have to shift it up by 1 unit because it's 1 minus, so shift up by 1 unit. So this will start from here. It's gonna go up and then down and then repeat. So this is the 2 pi. So basically I'm shifting by 1, let's be more accurate. Shifting by 1, so this graph is being shifted. So the horizontal axis is shifted and everything is shifted. So this would be the pi over 2 now. This would be 3 pi over 2. And this one here will be pi. Now, is this do you think this is a hard or an easy one? What do you think? Let's analyze it. If theta is 0, r is right here. It means if I plug in 0 for theta, my r is 1 minus 1, which is a 0. At pi over 2, it means when theta is pi over 2, my r is 1. And in between, what's really happening? My r is just increasing. So this distance here is increasing. So this distance is increasing. So the r in this part of the graph is how far we are from the origin. That's really what my r is. Now, at pi over 2, this should be 2. At pi over 2, I am at 2. So this point is the point 2 pi. And r is just increasing. So r here, when theta cover this region, my r does this. Now, at 3 pi over 2, I am right here. Between pi and 3 pi over 2, my r is decreasing. So my r is right here, and it's getting less and less. So it was at 2, right there. Between 3 pi over 2 and 2 pi, my r keeps decreasing. At 2 pi, I am at 0, and that's the picture. And as you expect, this is called a cardioid, simply because it looks like a heart. All right? Any questions before I move to the last part of idea that I will cover? So let's move on. And I will put the notes after I finish, because I actually want you to interact with me. I don't want you to read anything from Blackboard. But the minute I finish, I have them written already. I will put them on Blackboard for you. Now, the last idea is area of regions, given where the graph is given by a polar equation. Okay, so area in polar coordinate, if you want, given in polar coordinate, which is section 10.3 in your book, I think. Yeah, no, 10.4, whatever. Now, here's the thing. My problem is we have a region that's theta equal to 0, theta equal pi over 2, so I am in the plane. And I have here like a region, something like that. So this is the graph of r equal f of theta. And this is, I call it the line theta equal A, and this is theta equal B. It means from here to here, I have A, and from here to here, I have B. So it's just like, let's say, cardioid. If this is a cardioid, this is the graph of r equal 1 minus cosine theta. And suppose I'm interested for theta between 0 and pi over 2. It means I'm interested, this is my graph. Now, what we are interested in this, so this is the region. We're interested in this region. Actually, this region. So it's the region which is bounded by the graph of a polar curve. It means given by a polar equation. And the two lines, theta equal A and theta equal to B. And the question is, what is the area of this region? Okay. So it's like back to this problem here. So suppose here I tell you, okay, between 0 and pi over 4, let us say, suppose this is pi over 4, what's the area of this region? That's really the type of questions we are interested in. So what is the formula? What's the area? Okay, I'll give you the formula and I'll talk a little bit about where it comes from. So it's the integral, half the integral. So of f of theta square, so simple, so this is your function, and f of theta square d theta, so the variable will be d theta, and theta will go from, the lower limit on theta is where theta start with, and the upper limit is where theta finish. Okay. The formula is simple. The problem we're going to be facing is actually what's A and what's B. That's the problem that's going to be hard in this particular idea. A few words about where this formula comes from. A few words. I will not talk a lot about it. A few words about it. When we talked about graph of function, if you guys remember, you better. Regular function, x, f of x. To be able to find the area for this piece, we actually cover it by rectangles. Rectangles, 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 rectangles. To be able, and we added the sum of those rectangles to find the area. And that's where we end up with integral of f of x dx. The f was the height, the dx was the width, and we add those up. So AB. Now, if we have a piece like this, covering it by a rectangle will not work because I don't have the height. It's actually a very difficult problem. So what is the idea of basically how to find the area of this region? And the idea is the following. Instead of covering this with rectangle, we cover it with little sectors like this. That's what we cover it with. So we take theta from A to B and we divide the angle in pieces and we cover it with those type of region. Now, what's the best, why those type of region? Because there is a formula that you guys probably saw in middle school or somewhere that does the following. If you have like a circle, so it means a fixed radius, radius, I will call it big R, radius, and you take a piece of it, like that. Then, suppose I call this angle beta, and the area of the sector is a half times the radius squared times the angle at the center. So if you take a piece like this within a circle, the area is half the radius squared times the angle at the center. Now for this region, covering it with rectangle and adding is actually problematic because I don't know what's the height here. It's really, really problematic. So the idea is to cover it with those little ray or little sectors. And what's the area of a tiny sector? So the area of a typical sector will be, so area of a sector will be a half times the radius from here to here. So if I fix my theta I, the radius would be f of theta I squared. And the angle at the center, we're gonna call it the delta theta. And the idea is to add those, which will bring up the area of a sector. So that's in a few words, a little bit how this formula is derived. It's always a Riemann sum because that's what it is. And I cannot take rectangles because I cannot really find the horizontal or the vertical distance. So I will cover it by sectors like that. So let's practice this idea. So the area is, I rewrite it, it's a half times f of theta. Think of f of theta as the little radius because f of theta is r. It means how far we are from the origin. That's what f of theta is, times the d theta and a to b. This would be the problem piece. F of theta will not be a problem because it will be given to us. I will take two problems, an easy one and a harder one. So I will start with the easy one to set up the equation for us, and then I will do the harder one to be able to find how do we find the limit. The limit will be very difficult. So the first problem will be easy because I will give you the limit. So suppose I will come up with, let me take the curve r equals sine theta, and the question is find area of the curve bounded by r equals sine theta, and I'll tell you, will give you theta between 0 and pi over 2. So I very much just gave you everything in this problem. I always sketch, and you will see the importance of a sketch in the second example, but this one is easy, so I can tell you how to apply the formula. So how does the graph of r equals sine theta looks like? Okay, I always Sine theta is easy, so I take my Cartesian and I draw the sine theta. And actually, I don't need all of it because I only need theta between 0 and pi over 2. But sine is so simple. It goes up, down, up. So this is my pi. This is pi over 2, and so on and so forth. Now, in the polar plane, so that's my 0, that theta equals 0. And this is theta equal pi over 2. And I want to graph sine theta. So at 0, I am right here. At pi over 2, I am at 1. So as theta goes from 0 to pi over 2, r is increasing. Now, in this particular problem, I actually don't need to do the whole thing because I only want between 0 and pi over 2. But we can do it. From pi over 2 to pi, it seems to be like that. Between pi and 3 pi over 2, the graph is going to go back up here because r is negative. Between 3 pi over 2 and pi and 2 pi, this is the graph. So basically, this is the piece I'm interested in. That's the piece I'm interested in. And what's the area of this piece? So the formula is simple in this case because it's a half the integral from 0 to pi over 2, because I gave you the theta problem, very clear, times the radius square. The radius square. The radius here is the sine of theta. So the radius in terms of theta. So this is for every theta, whatever theta is, this here is the sine of theta. That's really how we saw. Every point here, the first coordinate in polar is the sine, the second coordinate is theta. So that's the theta. That's really what we're doing. And we're adding those little sectors. All right, now it turns out to be nothing more than a problem involving the sine. So this will give me a half of sine squared theta d theta. So computing those for this simple problem boils down to that. Now, how do we compute the sine squared? Just a little bit of a reminder. That's a sine, only even power. If you have only even power, you have to use the double angle, the half angle formula, which will give you 1 minus cosine theta over 2 d theta. Just to give you a head start how we do this. 2 could be getting out, and I will have the following. D theta. At this stage, that's a simple integral that we compute. Antiderivative of 1 is theta. Antiderivative of the cosine is the sine 2 theta over 2, evaluated between 0 and pi over 2. And that will give me a fourth. At pi over 2, I will have pi over 2. Sine 2 pi over 2 is sine pi, which is a 0, minus at 0, and I will get pi over 8. Okay, so now we will do another example, which is, as I said, a little bit more involved, and it will bring up, up front the idea of the limit. How can we figure out the limit? So problem number 2 is the following. I will take the area inside. So the question is find the area inside the small loop or the inner loop of the following curve. R equal 2 minus 4 cosine theta. So this is a problem where I did not give you the where theta vary from, like here. I told you just the small loop. So I have no idea what's going on. I have to figure out the graph. So I need to sketch the graph. So we do what we did before, which is a good review again for how we sketch. -2 minus 4 cosine. All right. We know how cosine looks like. 4 will stretch it by a factor of 4. Minus will flip it. And 2 will shift it up. So let us see if we can do that. I'm going just to lower this right there. So it's the cosine shifted up. So I'm going to put the line 2 here because that's the shift. And -4 cosine. So -4 cosine. So this is 2. It's going to start somewhere right here because it's the minus. And it will go up to 6. So this will go like that, like this. Now, if you forgot those problems, on the side, draw -4 cosine. This is -4 cosine. It's -4 here and 4 here. That's the minus. And then shifted by 2 units. That's really what it is. So this -4 will be shifted by -2. This 4 will be shifted up to here. This should be a 6. And then this point right here. So this would be my pi. This point right here, that's the pi over 2. This point right here is the 3 pi over 2. And this point right here is the 2 pi. Now I need to move. There is no way I can move without knowing this one and that one. I cannot move ahead. I want to know because I'm starting with -r. I have to know where I stop -r to move to +r because I'm changing equation. So I need to find those values. And the only way is to set r equal to 0. That's my r equal to 0. So this would give me the cosine of theta is 2 over 4. It's a half. And that will give me two values of theta. One is the pi over 3. And the other one would be the 2 pi minus the pi over 3, which will give me 6 pi minus whatever 5 pi over 3. So this point here, my first interrogation mark became the pi over 3. And my second interrogation mark is the 5 pi over 3. Now, this being said, we start the graphic. So this is my origin. This is theta 0. And this is my theta equal pi over 2. And now before I graph, what do you think I should do? What are the important lines that I should do? The important lines are when r is 0. So I have to draw theta equal pi over 3 and theta equal 5 pi. So pi over 3 is this line. And 5 pi over 3, which will be this one. Those are crucial for us to graph. So this is the pi over 3, and this is the 5 pi over 3. And now we graph as I've been doing. At 0, I am right here. That's important. That's -2, 0. At theta go from 0 to pi over 3, where theta is in this domain, r is negative. So r is right there. So it starts at -2, and then it's right there. That's my r. After that, it starts increasing. At pi over 2, I am at 2. It's increasing, it's behaving very well. At pi is gonna go all the way here. That's a 6. That's the 6 pi, still acting very well. Between pi and 3 pi over 2, at 3 pi over 2, I am at 2, and it's positive. So I am exactly in the same region where theta is. up to 5 pi over 3, I'm still positive, but it's heading towards 0. But then all of a sudden, it's negative. So it means at theta between 5 pi over 3 and theta equals 0, the graph is right there. So this is my graph. And now here's the question. They want the area inside the small loop. It means they want this area. So how can I find this area? So I let you look at the picture very well. So the area is the area. The area is half the integral. And this is where I'm going to struggle. Of the radius. The radius is f of theta. So this piece is not hard, square. This is the 2 minus 4 cosine theta. The piece I will be struggling with is this. Okay, and my question is, how can I catch this area? Theta should go from where to where? We can use symmetry. There is a lot of symmetry in here to be able to find this area. So now my question to you is, I want those. I want those. Those are the hard part sometimes. So I don't know. Anybody can pitch in. So to cover this, let's focus on the lower loop. And then I'll take care of the upper loop. Let's focus on this one, the one here. To cover this loop. So I'm looking at those. Theta should vary from where to where? 0 to pi over 2. Do you agree with Lori? I disagree. And I'll tell you why. Between 0 and pi over 2, it means that theta go from here to here. What kind of a graph we have? We have this piece of the graph and this piece of the graph. That's what happened between 0 and pi over 2. Because r up to pi over 3, this is my r, and between pi over 3 and pi over, okay, all right. So 0 to pi over 2 is wrong because it will give me this piece and this piece, which is not what I want. So I need other suggestions. Okay, Sarah, do you agree with Sarah? Sarah is taking me from pi over 3 to pi. Let us think, what do we cover between pi over 3 and pi? I want the small loop. Between pi over 3 and pi, this is the piece I'm covering. Is this the small loop? Joseph, 5 pi over 3 to, so you're going all the way up to here, Joseph, right? This will I accept because what Joseph is saying, he told me from 5 pi over 3, this is 5 pi over 3 to here, which we will be covering this piece, the top one, and then keep going one more turn, and then you actually cover the lower one. This is correct. This is correct. Anybody have any other suggestion? Use symmetry a little bit. Let us use symmetry and focus on which one? On the upper loop. Okay? I don't know, you can focus on any one of them. So I will draw. I'm going to work along Joseph's idea. That's why I picked the upper loop. Suppose I want to catch this loop. Theta has to go from where to where to be able to get this piece. I actually read it. If theta between 5 pi over 3 and 2 pi, when theta vary from here to here, that's how I am obtaining this loop right there. So One possibility would be those two loops have the same area. So let me focus on the upper loop. The upper loop is obtained when theta goes from 5 pi over 3 all the way to 2 pi. I will get the upper loop. Sorry, that's the upper loop. So to get the upper loop, where my theta should go, I look at the picture. How did I get the upper loop? I got it between 5 pi over 3 and 2 pi. So from 5 pi over 3 to 2 pi, I got this piece here. So that's where we give me the upper loop. The lower, I just multiply the whole thing by 2, and I would get my problem. So let me fill in the details now. So the area will be one possibility, because there are a lot of possibilities. The area would be equal to, and actually I'm going to rewrite this so I don't have to rewrite. So the area is twice times the area of the small upper loop. And now what about this? What's the area of the upper loop? It's a half times the integral. To cover the upper loop, theta has to go from 5 pi over 3 all the way to 2 pi of 1, sorry, I forgot what I gave you, 2 minus 4 cosine theta square d theta. All right. Anybody has any other suggestions? It means, oh, so that's one possibility correct. Another possibility is what Joseph said. Joseph said go from 5 pi over 3 to basically 5 pi over 3 plus pi over 3. Then you get to 2 pi and add another pi over 3, and then you cover the whole loop. So the way Joseph thought, it start at 5 pi over 3 all the way to 2 pi. You get the upper one, and then from 2 pi to 2 pi plus pi over 3, you get the upper one. But this will give me 7 pi over 3. So that's another possibility of d theta. Okay. So I'll ask you one more question, and then of course we go. My second question is, let's see if this is okay. Suppose I ask you to find the area of the large loop. This one. Upper large loop. Okay, how do you think about it? Ask yourself, to cover this large loop, my theta has to go from where to where? So if I want to cover this large loop, all of it, where should my theta vary? And we close at this point. All right, any suggestion? So you look here. The way I think about it, I look here and I look here. How did I get the large loop? My theta has to go from where to where to pick up all of the large loop. I'll let you look at it. Okay, so if I want to pick up this piece of the curve, theta went from where to where? Look at here. How did I pick up the large piece? Where did my theta vary? That's what it varies. So when I went from pi over 3 all the way to 5 pi over 3, it means when theta went from this all the way to here, that's how I picked up the large loop. So to find the area of the large loop is going to be a half Right here has to be the pi over 3. And right here has to be the 5 pi over 3. So you ask yourself for those questions to find those limits. You go back here and you said, how did I cover? Which value of theta I needed to cover the large root, to cover those, besides my R's. So from here, I realized to cover this big loop, my theta has to go from pi over 3, not from pi over 2. It has to start from here all the way up to here. Okay. All right. I will assign problems for tomorrow, and this is the only hard part in this area thing, is that we have to figure out those upper limits. I will assign problems for tomorrow, and this will be actually the last thing I will do. So we'll have plenty of time to work on that tomorrow. And if we have time, going extra time, I will start reviewing with you for the final. I have an idea which one that you guys have forgotten that I will review with you. And that's it. Do you guys have any questions? You're very quiet today. Any questions? Okay. I'll see you tomorrow. Please try the homework. You may struggle a little bit, but we will take care of that tomorrow. Bye-bye, guys.